The broadcast is now starting. All attendees are in listen-only mode.
All right, good morning, everyone, and welcome to the September California-Nevada Drought and Climate Outlook Webinar. Thank you that have joined us previously and those that may be joining us for the first time. My name is Amanda Sheffield, and I am the Regional Drought Information Coordinator for NIDIS in California, Nevada. And we've hosted these webinar series actually coming up on 3 years right now, bi-monthly, designed to provide the region with timely information on the current drought status and associated impacts, as well as a preview of developing climatic events. This webinar is co-hosted with the NOAA RESA team, the California Nevada Applications Program based at Scripps and DRI in Reno. Today we've got a great webinar set up for you today. I will be giving the Drought and Climate Update, and then we have two great speakers today. Eric Bolt, who is giving the Drought and Climate Outlook. He is with NOAA's National Weather Service in Los Angeles and Oxnard. And then we have Sasha Gershinoff from CNAP and Scripps giving a presentation on their recent work studying precipitation regime change in Western North America, the role of atmospheric rivers. Before we get started, I just wanted to give a brief overview of NIDIS for those that haven't joined us previously. NIDIS's mission when we were created by Congress was to improve the nation's capacity to proactively manage drought-related risks by providing those affected with the best available information and resources they can to assess a potential drought and better prepare for and mitigate impacts. So we work to improve our understanding of how and why droughts affect society, the economy, and the environment, improve information accessibility, as well as build the foundation of a national drought early warning system. Here you can see we do this through regional systems, with California and Nevada being one of them. So for example, the California Nevada DEWS has a lot of ongoing partner activities and working towards making information usable and understandable for decision making. And these activities fall under 5 general areas of observation and monitoring, prediction and forecasting, interdisciplinary research and applications, planning and preparedness, and communication and outreach, such as this webinar. Just a few quick announcements or information tidbits before we get started. I just want to mention, many of you may have received this in email already. It was to save the date for the California Nevada DEWS partner meeting, which will be in Sacramento in November. The previous meeting we had was 2 years ago in Reno, but these meetings bring together all our different partners to share and discuss ongoing drought activities, learn about new drought research and resources, explore emerging issues, and think about collaborative pathways forward for us and our partners to work together to improve drought preparedness in California and Nevada. The few other things I wanted to let you know about before we got started was NIDIS has a busy summer, so I thought there might be some information that you guys were interested in. One of the things that Congress tasked us in the last reauthorization was to build a strategy for a coordinated national soil moisture network. And so the link here, and then I'll share these slides afterwards, is an article on moving towards that coordinated soil moisture network. And I know many in California and Nevada realize how important that data is, and so I encourage you guys to read that. In July, we hosted a national drought forum. You can find an article, a high-level article on drought.gov about it in Washington, D.C. that brought together the high-level leads of agencies, the private sector, nonprofit, et cetera, to talk about the emerging drought issues and things that we could work on going together. And then finally, one meeting that I was actually super involved with was a summit on drought and public health. This meeting built off different work we have with partners on connecting the two pieces of information, the two sectors, and as well as how can we move this going forward with groups like the CDC and local public health departments and things like that. And so there's also an article on drought.gov if you're interested. And so with that, I'll go ahead and get started. As I mentioned, I am going to be giving the drought and climate update before following by Eric and Sasha. All right, to go ahead and just jump right in. So here are the current drought conditions across the West, including California and Nevada here. I wanted to show the West at first here, because as you remember, the Colorado River Basin in California and Nevada got quite a bit of rain and snow this past winter. And so, for example, California and Nevada did not have any drought on the map as of March, I think I remember. But this summer, there has been a creeping a little bit of drought, this browner color here, to the southwest, especially, and to the southeast parts of California and Nevada, due to the lack of normal monsoon rains and as much as normal. So drought has entered here in the southwest, which has increased the amount of drought here in California and Nevada. Here's just a zoom in of that same map. So we have D1, moderate drought here in 4.19% of Nevada and just over 2% of California. And since we're coming up to the end of the water year, I thought let's compare that to where we were last year in the water year. Here, October 2nd of last year, where Nevada had, both states actually almost had about 50% of the state in drought, and how much last season did change things. The summer precipitation and temperature here. So these are both maps of here the departure from normal temperature over the last 90 days, so since the end of June. The redder or orange or yellow colors here are going to be your above normal temperatures. As you can see in a lot of California towards the coastal areas, we were above normal, and some parts of Nevada, though there were patches of below normal temperatures over the summer. And then obviously we tend to dry out and have a little bit less precipitation in our summer seasons. And so right now, though, our percent of normal precipitation here on these bright red areas are 5 to 50% in a lot of the southern areas, whereas there were a few storms up here into the northern part of the area. So over the summer, we generally were more dry in the central and southern part of the region. Just to tie to that, because I think it ties, they've been using this information to, I think, thinking about the drought monitor as well as other drought indices. I wanted to show summer evaporative demand drought index. So this is the 3-month index, though you'll see very similar trends in the 1-month or 6-month timeframes of the atmospheric thirst of the atmosphere. Evaporative demand uses relative humidity, solar energy, wind, and temperature to think about how the atmosphere is thirsting on what water maybe is lying on the surface. And you sort of see these areas where the lower precipitation, well, it's actually the higher temperatures were, as one of the factors, there is higher evaporative demand here, and especially here in southern Nevada. But generally, we were doing pretty well in the region with all these blues and white colors, and not having a ton of evaporative demand in the region. Now look back over to the water year. These two maps are going from October of last year to August of this year. Here, the temperature percentile and the precipitation percentile. Not surprising from last year's wet winter. Over the entire year, when you add it all together, we are above normal, much above normal, and little small patches of record wettest across the region. And overall for the year, we are above normal temperatures here, especially of California, western Nevada, with cooler patches out here in eastern Nevada. Just to wrap up the water year, I was looking back at how our snowpack evolved as well as reservoir levels. Here's a map from CNAP, the NOAA RESA team, courtesy of Mike Dettinger, going back to October 1 of last year, going through July 1 of over the summer. The blue here is what the reservoir normals are, and then the gray here is what those reservoir totals plus snowpack typically are. So typically in a year, we would have about this much reservoir and this much snowpack. And so this year in 2018, the red shows the reservoir levels increasing with time due to all the precip and snowmelt we had, as well as when you combine looking about them, the reservoir and snowpack together in this orange line, which was above normal, and towards the end of July melted out completely, but left us above normal here in our reservoir totals for the year. You can see that now jumping towards this just the other day in our reservoir totals. Here's for California from the Department of Water Resources, the major reservoirs. This red line here is the historical average. You can see most of the reservoirs are above or well above, in some cases, that area. On the left here are two images. For example, I took myself, I went on a Water Education Foundation tour the other week. And this is Pyramid Lake and Lake Achuma on the central coast, showing how well they're doing in terms of their levels. They're not represented here on this map. And then to look at Lake Tahoe as well, here starting in October of last year and how it increased throughout the season. And when you compare that going back to 2012 or the drought years of 2014-15, this is what this figure is showing here, is how well we're still doing in terms of Lake Tahoe levels as well. And just want to add a little bit of detail here in that we have been obviously a good summer. The snowpack lasted longer. Precipitation is also impacted greenness. So these are two maps. Here on the left is actual NDVI, the vegetation index. You see a lot of green areas, and I compared that to difference from average. So what do we normally see? And as you can see in California and Nevada, we're seeing a lot of green still across the different areas. And so this was the 60-day average of greenness. And if you look at shorter time frames, it's still relatively green as well, except for in different patches of redness. And so we've had lasting greenness throughout the summer as well. Currently, I just want to also say I'm not an expert in this, but people are interested in the current large incidence of wildfire happening. As you can see the source here if you'd like to follow the map, but we haven't had a ton of cases this year. The largest one I was reading so far has been here, the Walker Fire thus far. Just to touch a little bit on the Colorado River Basin, because some of our water supply does come from here. These figures are from a Metropolitan Water District, this great flyer they have, which summarizes all the different pieces of information from their water supplies, which includes the Colorado. Here are two figures, for example, for Lake Powell storage and Lake Mead storage, which according to this Lake Powell has 2.17 million acre feet more storage than it did this time last year, and Lake Mead has 388 TAF more this year than last year. So we're still very close to the shortage trigger on Lake Mead storage, and then they've been looking at forecasts already out to 24 months from the Bureau of Reclamation. And then lastly, I think I'm just going to briefly mention the Northeast Pacific Marine Heat Wave that's going on right now. You may have heard called this, they're comparing it to the blob that we had in 2014. They've been developing in very much the same ways, and they're calling this now the Northeast Pacific Marine Heat Wave of 2019. It's basically the ridge of high pressure has dampened winds and haven't quite mixed up that ocean surface as much as normal. And as of right now, it's about 3 degrees C above average in its warmest place, and it's about the second largest marine heat wave in the last 40 years. And so while it is looking similar to what we've seen in the past, we are going to have to continue to monitor it and see if what storms and what may break that high pressure system, et cetera, that's contributing to that warm layer on the ocean, see whether it's going to last or not. And that I'll just summarize. So we currently, because of some of the due to the dryness in the Southwest, small areas of moderate droughts in the Southeast, California and Nevada, generally above normal temperatures for the past 90 days and the water year, and dryness in the central to south part of the region. As we go into the new water year, we do have above normal reservoir levels and a lot of greenness. And I forgot to mention on this other slide that there is a NOAA tool here for tracking these type of blob events, and I recommend you check it there. Either the link here or just search for NOAA California Blob Tracker or something like that, I think, to be able to stay up to date with what's happening with the blob. And with that, I will stop and go ahead and pass the presentation over to Eric if you're ready.
I'm ready when you are.
Great. I forgot to mention that if you have a question, feel free to enter it into the questions box. I will try to do quick questions in between presentations, but most of the questions we'll answer towards the end.
Okay, does that look okay, Amanda?
Yep, you look great.
All right. Good morning, everyone. Thank you for joining this webinar. I'm Eric Bolt. I'm the Warning Coordination Meteorologist for the National Weather Service Los Angeles office. And we do get quite a few questions about El Nino and whether or not we're going to have that every year. So I'm glad to participate in the webinar today. One of the slides that Amanda already covered was precipitation during the summertime, and this is just looking back at the last 90 days worth of precipitation. You can see there in the red, less than 10% of normal, a little bit higher up in Northern California. Very typical for the summertime, although we've been not seeing a whole lot of monsoon conditions, very limited activity over the summertime. So even less than normal for precipitation during the summer, but definitely Mediterranean climate, we don't expect much precipitation during this time frame. So not a big deal overall for the summertime rainfall. And then I think Amanda already covered these, so it's kind of interesting how we look at the same information, but definitely if you look back to the water year, going back to October through August, we still are reaping some benefits there as far as above normal precipitation in most areas, and even some record-setting conditions there in Nevada. So just a refresher again about we still see some good water recovery because of the rainfall last winter. And then temperatures, much like we've seen in the last, almost 2 decades now, every year we're seeing above normal temperatures, especially in the West Coast, although looks like Nevada did stay a little bit below normal for this last season on temperatures. And then I just wanted to show kind of a loop here of the sea surface temperature anomaly, and this starts in July and loops through to September. And I've also kind of highlighted the area that is really watched for El Nino conditions, and that's that purple box labeled as Niño 3.4. That's where they're looking for any type of anomalies for decision making on if we're going to head into an El Nino versus La Niña. And if you just kind of watch the loop there, you can kind of see a variation of above normal and below normal temperatures, especially as we go into the later part of the loop. So conditions are cooling off the coast of South America and over into the central tropics. And that's why we're headed out of any type of El Nino signature toward neutral at this point. Other places there in the Pacific, you can see all that warming that Amanda talked about, and temperatures running a good 4 or 5 degrees Fahrenheit above normal. And that's part of this area of concern for heating, as well as the Arctic area. You can see how brightly red that area is. And the blob, very scientific name for this area of heat that generates itself over the Pacific. And if you remember, this was all because of high pressure, just kind of sitting in the same spot, kind of deflecting storms or weakening them quite significantly as they move through the Eastern Pacific. So that warm water just sits there and continues to thicken up and expand. So back in the 2013 to 2015 years, we really, that was the core of our drought conditions, and that was because of this blob kind of blocking and weakening storm systems. Recently, this month, I've seen several different headlines about what's coming up this year, and the quote there, or the headline on the right, was from the Washington Post just a couple of days ago, the most recent headline about the blob and some of the impacts it may have to marine animals and mammals, and also our weather patterns. So it's something to keep an eye on. There's a lot of concern, but it's a different scenario at this point. It's not nearly as deep as it was back in 2013 and 15 years. So just something to be thinking about, and you'll probably hear more about that as we get into the winter months. This is kind of a look, I just kind of remembered I had captured this, kind of a composite of all the different storm tracks for the winter in 2014, which was also a neutral year. And you can see that high pressure area just kind of sat there in the Northeast Pacific Ocean, really blocked storm systems from coming into the West Coast, and a big reason for our drought conditions back then. So the latest INSO information is looking like this. We're currently in a neutral condition, so neither La Niña or El Nino. Definitely that Pacific Ocean water temperatures remain above normal. Here in the South California coast, we have ocean temperatures are actually kind of nice this time of year, 65 to 75. Sorry about that. And we do see, and what the consensus is a 75% chance of this neutral condition this fall, and then at least a 55 to 60% chance of that persisting through the winter months. And this is the plume, again, that ENSO 3.4 region over the tropics, and this is the area that they really look at for deciding what's going to happen over the winter months. So the left side of the chart is current conditions, and then all those different lines show the forecast going out through the winter months, and they all kind of straddle that 0 to maybe 0.5 degree temperature anomaly, and that's right at neutral conditions. So most of the agreement is to stay in neutral for this winter. And what does that mean for California especially? And this pretty much includes Nevada as well, but majority of the time during the neutral condition, you can see those different pie charts there, we're drier than normal. There's occasions where we do have above normal, and I put a couple examples here. 26 inches in Los Angeles back in the early 90s, and then the northern Sierras had water equivalent of nearly 95 inches in 2017, which was also a neutral year. One reminder, though, it only takes 1 or 2 storms to create all of our flood issues here in California. And so that's something to always watch out for any year. Also wanted to show this for downtown Los Angeles, since I am from the Los Angeles office. The center area there are all the different neutral winters and the gray bars, and the purple line is basically the water average during the wet season. So we usually fall just below that, maybe around 12 inches of rain overall throughout the history, going back to about 1950. So when you're looking at the neutral conditions across California, it's pretty much leaning toward the drier side. And this is our official outlook. So our Climate Prediction Center back east provides these long-term outlooks throughout the winter season, and this is what they are showing. So this is for the month of October. It's kind of a 1-month outlook, and anytime you see no significant green or brown over California and Nevada, that pretty much means equal chances of just about anything. We could have below normal, above normal, or equal kind of normal precipitation for the month of October. And they do show a little highlight there in Arizona, maybe the far southern piece of California for the month of October. Looking further out, we can go 3 months at a time. This goes November through January. You can see that now we're starting to see this bias toward a below normal precipitation, maybe in some cases over 40% chance there along the central coast of California, even some of that spreading into Nevada for the early part of the winter. And then the core of our wet season is January through March, and you can see there's not a whole lot of change. If I go back one here, November to January, January to March, basically the same scenario is favored, kind of on the drier side, and that could impact those Sierra mountains as well for our precipitation this winter. Temperature-wise, no big surprise. Like we've talked about, above normal seems to be our trends, and that continues. So November through January, higher than normal probability of being above normal on temperatures, and that continues along the West Coast through the bulk of the winter time. So even during a neutral year, we're looking at above normal temperatures expected throughout the region. And just a seasonal drought outlook. This is something that our agency puts out every few months, and you can see this goes through the end of the year. And really no change. If you remember back what Amanda showed there, the far edge of Southern California and Nevada, just pretty much remaining the same, at least through this calendar year. So the reminders I like to tell people is California winters and Nevada winters very highly variable. It only takes a few storms to cause significant flood issues, even in a wet or dry year. The atmospheric river events are our big events, and those sometimes give us our highest threat of flooding, and our next speaker will be talking about that specifically. And then the ENSO neutral winter is definitely going to tilt the odds toward below normal precipitation across California and Nevada. So that's all I have. Hopefully that gives you an idea of what to expect this upcoming winter.
Great, thanks, Eric. We have one quick question while I'm changing slides. Can you speak more about the PRISM data source?
The PRISM data?
Yeah.
Mainly that's just being a good measurement by month or water year for precipitation across the region. I don't know the specifics behind it, but it does give us a nice spatial view of what's happening precipitation-wise across the region.
Great. And then our next speaker is going to be Sasha Gershinoff, who's from Scripps.
Oops.
Nope, we could see your PowerPoint.
Can you hear me now?
Yeah.
I was muted.
Yeah, we can hear you.
All right. Okay. Yeah, my name is written Alexander, but it's pronounced Sasha because Sasha is nickname for Alexander, where I come from, and they speak like this in this very large and aggressive country. But in any case, I've been in California long enough, 41 years now, to talk about this. And I will give you a longer term perspective on the future okay, hold on. I'm trying to get my screen here. Okay, can you see it?
Yep, we can see it.
Okay, so basically, I want to give you a perspective, kind of a mechanistic perspective on precipitation regime change projected by climate models for the next decades. And I'll start with this global picture. This is the projected change of total annual precipitation by about 30 different global climate models. So it's basically late 21st century precipitation minus the late 20th century. And what you see here is precipitation is increasing, projected to increase in most places where it's green, and where we have these dots that shows agreement between climate models, basically where 2/3 of the climate models, 20 out of the 30 models, agree on the sign of the change. So that's where we're confident that precipitation will increase over the tropical belt and the extratropics, especially the high latitudes. And that's basically because the atmosphere is getting more moist as the ocean atmosphere, as the climate system warms. But the dry regions, in the subtropics, are clearly also projected to dry. And I point your attention to these so-called Mediterranean climate regions, like the Western Cape of South Africa, parts of Australia, this part of central and southern Chile, and of course the Mediterranean basin, are all projected to dry. These are all regions that sit on the boundary of the subtropics and the mid-latitudes. So they have subtropical dry summers, and most of the precipitation comes from mid-latitude storms in the wintertime. These are also regions where wine grapes prefer to grow in. California is one of these regions, but we get a sense that the models don't agree on the sign of the change. At least that's the case with total annual precipitation. But of course, precipitation is generated by quite a small handful of events in this region. We really have to look at daily precipitation to understand what's going on and whether, in fact, there is no signal there. So in one recent study, we isolated these 5 Mediterranean climate regions around the world Here's California, and we basically looked at how precipitation is changing specifically for those regions. And you can notice that they're all projected to dry from the equatorward side, and California is no exception there. And this is really this drying from the equatorward side in these Mediterranean climate regions comes from the fact that the subtropical belt is expanding. That's clear from the observations and model projections, and basically as the subtropics expand, the dry season expands in these regions, and it pushes out the wintertime storms, especially in the early and late wet season. So in the fall and spring, in our case, and down here you can see that pretty much all the models agree on the drying for the Mediterranean, South America, South Africa, and Australia. But in California, the spread of model projections is quite large. Some models go wet, others go dry. So let's delve into that and see why that's happening. So here we've binned precipitation, daily precipitation now, according to the intensity of the daily precipitation. So here we have on the left the dry day bin, so 0 precipitation, and you can see that the frequency of dry days is projected to increase in most of these regions. And here we have drizzle, basically the weakest 10% of precipitation events. And then as we go to the right, we'll basically go to higher and higher intensities through low and medium intensity categories, where the frequency of precipitation, low and medium intensity precipitation, is clearly projected to decrease, and then towards high intensity heavy precipitation here above the 90th percentile, and then extreme precipitation above the 99th percentile. So these are the 1% of the most extreme precipitation events are clearly projected to increase in frequency as well as intensity in California specifically, and to some extent the Mediterranean basin. The Mediterranean basin, this increase in heavy precipitation events, extreme precipitation events, is not enough to offset the decrease of precipitation due to the loss of sort of your run-of-the-mill medium to low intensity precipitation. We know, so let's try to explain specifically for California, what is it that sets California apart, and why is it that that California is so different? And really we can see here it's the extreme precipitation that's projected to offset the decrease from losing the low and medium intensity storms in California in the early and late wet season. Okay, so let's try to explain why extreme precipitation is expected to increase in California. Well, we know that extreme precipitation in California is typically delivered by atmospheric rivers, and here we have a snapshot of atmospheric moisture from satellite on a particular day. And you can see that most of the moisture in the atmosphere is in the tropics, but then there are these thin filaments of very moist and windy conditions as well that are called atmospheric rivers that basically, there may be about 4 to 7 of these around the globe at any particular time. And they don't cover a lot of the area, maybe only 10% of the mid-latitude area, but they actually account for about 90% of the transport of tropical moisture to higher latitudes. And as these atmospheric rivers, so very moist, windy filaments, corridors of moisture transport, when one of these makes landfall, and here's one making landfall at the coast of California, that that moisture at low levels is slammed against the coastal ranges and the Sierra Nevada, and basically forced to rise, and we get and it's squeezed out of these features, and we get orographic precipitation, basically due to these very moist air being forced to rise over the topography of the region. And in California, actually, the topography is oriented perpendicular to most of these atmospheric river landfalls. So it's very effective in squeezing the moisture out of these atmospheric rivers that account for about, I don't know, 40 to 50% of the total precipitation in the region. And for example, in Northern California, atmospheric rivers account for over 50% of total annual precipitation, but there are not that many of them, and basically they tend to be heavy precipitation events, and so it's in these few extreme events that would generate a bunch of our precipitation, most of our precipitation, at least in Northern California and over the Sierras and the coastal ranges. You can also see the transverse ranges amplifying the precipitation out of these. The person pictured here is the one that produced most of these results, and she comes from a place where no atmospheric river has ever made landfall and probably never will, right here in the middle of the largest continent on Earth. So here I'm showing a so what we did here basically is apply our atmospheric river detection methodology to 16 different climate models. And these are the climate models listed here in the left column. And basically, we've looked at a bunch of different variables: frequency of atmospheric rivers, frequency of days with atmospheric river conditions, duration of atmospheric rivers that we call ARs, and average intensity and maximum intensity of atmospheric rivers. Well, the maximum intensity is something I'm going to focus on because that's what's related to extreme precipitation events. And we're basically looking at the historical period for all these variables. So the last half of the 20th century, the projected future, the last half of the 21st century, and the difference. And I'm going to show these differences. And also notice that there's quite a large spread in model projections, but they're all trending up. So from about 20% to about, I don't know, 84% is the spread. That's by how much the frequency of days with atmospheric river conditions is projected to increase. But then we also validated the models according to their ability to reproduce atmospheric river landfalls in the most realistic way. And these 5 models are highlighted here. And if you look at these changes projected by these 5 models, you can see that the uncertainty has shrank quite a bit, very significantly, actually. So how did we validate these models? We looked at a couple of different things. One is the seasonal cycle of atmospheric river landfalls. And basically what I show here is months from July to June. And this is pretty much the atmospheric river landfall season. And here we have latitudes from 20 north to 60 north. So you can see that atmospheric river landfalls are most frequent in Canada and the Pacific Northwest, starting in late summer and basically in early fall. And then by winter time, this is December right here, atmospheric river activity migrates down the coast to Northern California latitudes. Typically, and we can see how how this seasonal cycle of atmospheric river landfalls is reproduced by different models. And here's one example, basically, of a very realistic model in terms of its portrayal of the seasonal cycle, but the atmospheric rivers are a little too moist in this particular model. And we can basically compare. I'm not going to get into details, but we can see how realistic these patterns are in every model. And what we're showing here is spatial correlation, so how realistic this pattern is, and also the root mean square error that shows the bias of the overall bias of atmospheric river intensities. And what we want is low error but high spatial correlation. So these models in this corner here, in this right bottom corner, are the most realistic according to this criterion. We also looked at another criterion where we basically look at the contribution of atmospheric river activity to total annual precipitation. This is from observations on the right here, and this is from that same model again. You can see that it looks pretty realistic. We basically applied the same sort of validation exercise to that and come up with 5 models that are the most realistic. And those are the 5 that I highlighted in the previous slide. And this exercise, this validation exercise, actually resulted in a decrease in uncertainty of the full projection of the full ensemble. And we can see now that what I'm showing here is the maximum intensity of atmospheric rivers at landfall for the west coast of North America. And in red, I outlined the mean of the 5 most realistic GCMs. But basically, all of the GCMs, including the less realistic ones, show an increase in atmospheric river intensity, pretty much emerging, with the trend emerging pretty much right now in the beginning of the 21st century, and then continuing and accelerating somewhat through the rest. This is the business as usual scenario that these climate models have been run under. Okay, well, what does it mean? What does this increase in atmospheric river activity mean for the contribution of atmospheric rivers to total annual precipitation? So here it is from those 5 most realistic models in the past, so the last 50 years of the 20th century. Here it is for the future, the last 50 years of the of this century, and here's the difference. And so basically, what this shows is that the contribution of atmospheric rivers to total annual precipitation is projected to clearly increase, and this increase is the strongest in California, where the mountains are oriented ideally to squeeze moisture out of these atmospheric rivers. And of course, as this is not a big surprise, because as the climate warms and warmer atmospheric rivers carry more moisture, that larger amount of moisture slammed against the same mountains is going to produce more precipitation. Well, let's look quickly at basically what is the contribution of atmospheric rivers to this picture that I showed you before, where I showed a projected decrease in the frequency of low to medium intensity precipitation, and then a projected increase in heavy and extreme precipitation, specifically in California. So let's focus here on the Russian River Basin. I'm showing 3 basins of flood-prone rivers along the west coast, but they're basically showing the same pattern. So this figure that I showed you before is repeated here in the dots. Basically, the black dots show the projected changes in of precipitation frequency in these different intensity bins, and you can see again this projected decrease in low and medium intensity precipitation and increase in high and extreme intensity precipitation events. And then the dark shaded bars show the contribution of atmospheric rivers to that change, and the light shaded bars show the contribution of all the other storms, basically mid-latitude frontal cyclones, to that change. And you can see that the non-atmospheric river storms are responsible for this decrease in low to medium intensity precipitation, whereas the atmospheric rivers are pretty much wholly responsible for the increase in heavy and extreme precipitation events. So this larger contribution of atmospheric rivers to total annual precipitation really means a change in the precipitation regime where maybe the total is not really going to change that much necessarily, but it's going to come from fewer but heavier, more extreme storms. So a flashier precipitation regime. And this is a region that already has a very flashy precipitation regime, here it is depicted by Mike Dedinger, where he basically took station precipitation measured at meteorological stations, and he computed the year-to-year variability of the total annual precipitation and divided it by the total climatological average precipitation. And you can see that, for example, in the east, the year-to-year variability is about 10 to 20% of the total average. That's really because it rains most of the year there. It precipitates most of the year. So you have a very large sample of precipitation events that make up the annual total. A large sample goes with small sampling variability. As you go to the west, you know, we end up in California, where, especially in Southern California, where precipitation is least frequent, we have the largest year-to-year variability of volatility of precipitation and water resources, up to 70% of the total annual precipitation. So it's really the fact that precipitation is so infrequent here that explains why there's this year-to-year sampling variability that is so strong. Everything depends on, you know, whether a year is wet or dry. It depends on whether we get that one or two really big rainfall events in Southern California. What happens, so we can basically repeat this analysis in the climate models. So here I show the variability of year-to-year variability of total annual precipitation divided by the total annual precipitation in the past. Okay, and this is very similar to what we saw from Mike Dedinger's plot here. You know, up to 60-70% of the annual total, we can get these large swings that are typical. We almost never get the climatological average in terms of our precipitation, at least, especially in Southern California. Well, in the future, this variability certainly increases as we get precipitation from fewer but more extreme events, and everything becomes even more dependent on those large, whether we get those large events or not. And here's that difference. Basically, the projected increase in the volatility of water resources and the variability of the total annual precipitation from year to year, the interannual variability of precipitation in the future, that's really due to this decrease of the sample of storms that produce our total annual precipitation, which is already small in this region, and that's why it's so variable, and it's projected to become more variable, and very clearly so by pretty much all of the climate models. And I'll leave you. So I'll leave you with these with this summary. But since we're on a drought webinar, I'd like to, and I've been talking about extreme precipitation. What I'd like to point out is that with this type of precipitation regime change, where more and more of the total annual precipitation depends on fewer and fewer extreme events, this increase in the year-to-year variability of total annual precipitation basically means that there's more opportunity for flood as well as drought. And I think the last 20 years or so have been a great example of that, where we've only had really 4 wet years. The rest of the years were dry. This is what is projected to be exacerbated. This type of volatility in our hydroclimate is projected to only get larger. And I think I better stop here.
Great. Thanks, Sasha. There is a question. Is there any temporal trend of when atmospheric rivers will make landfall? For example, more early or late storms in a given year for California?
Well, specifically for atmospheric rivers, we see atmospheric river activity intensifying, and it's really because atmospheric rivers become wetter, longer, and fatter, and so they last longer, they're more extreme, and their season may also widen somewhat. However, the other storms are getting shrunk to the peak of winter. So atmospheric rivers in California tend to occur at the peak of winter anyway. And I think what we're looking at is a narrower wet season that's becoming gradually more and more dominated by atmospheric rivers at the peak of winter.
Great. Thanks. At this time, I'm going to let people enter their questions. Thank you, Eric and Sasha, for your great presentations. While people are all typing in their questions, and I see at least one other already, I just want to remind folks that a recording from this webinar will be available on the NIDIS YouTube within probably a couple of days, and then also the 2-page webinar summary will be on drought.gov later as well. Our next webinar is scheduled for Monday, November 25th, and you can find registration already open on drought.gov. Just go there and click on the calendar. And then I think, Sasha, this is another question for you. Do you have a tool online to see where the atmospheric rivers are at any given time?
Yeah, definitely. It's go to the CW3E website. This is the Center for Western Water and Weather Extremes at Scripps. I collaborate with the center and provide climate scale information about ARs, but they have an excellent tool to visualize atmospheric river landfalls as they occur, and there are also forecasts available on that website too. Here it is.
Yeah. Yeah, I just pulled it up real quick. If you just go to cw3e.ucsd.edu, you'll find their monitoring tools, but also right here, their atmospheric river forecasts, and it'll explain this graphic, which is the forecast they have.
And there are many different formats for the same information actually available there.
Okay. I don't see any other questions, so at this time I'll go ahead and end the webinar. Again, thank you everyone for joining us. We hope you found this webinar was informative. When you do close out the webinar, there is a little post survey, so if there's some information you'd like to see next time or tell us how we're doing, we gladly take that information. And if you would like to get more information or be more involved with the California Drought Early Warning System, please let me know. My information's right here, and thanks, and hope you guys have a good week.
Thanks, Amanda. Take care.
Yeah, thank you, Sasha.
Thank you.
Thanks, Eric.